Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. Now, in Module 6, we can talk about memory management. Memory management is a very big part of the operating system. Now, the section 6.1, Requirements for Efficient Memory Management, and this is a relatively big section, so we're going to split this section into two parts to reduce the size of the video. So the first part is section 6.1a. Now, in the earlier chapter, we mentioned that the operating system is a computer software that is designed to manage the computer hardware. Now, memory management is a very important part of the operating system that is designed to manage the computer memory. Okay, so now what is a computer memory? So sometimes the computer memory is also called a computer's physical memory, or we call RAM, RAM, which is actually standard for random access memory. Now, RAM is a hardware structure consisting of linear sequence of words, okay, that hold a program during the execution. Now, we mentioned a word. What is a word? A word is a fixed-sized unit of data. Now, computer memory is going to store the data. So, word is the smallest manageable unit in the computer memory. A typical word size is 4 bytes. Now, just keep in mind that the computer system used the binary numbers. So the memory size is also measured using the binary numbers. So 4 bytes is basically 4 times 8, because each byte represents 8 bits. Each bit is just one digital that can store 0 or 1. It's a binary, so it's only 0 and 1. So 4 bytes is basically 4 times 8, 32 bits. Okay. But the word size could be smaller. It could be single byte, so which means it's 8 bits. Now the word sizes basically depend on the computer system. Now the earlier computer system was less powerful. The memory size was small, so the word size was relatively small. Now, as the computer actually becomes more and more powerful, the word size becomes bigger and bigger because the memory size becomes bigger and bigger. Okay. Now, the other concept, the physical address, is used to identify the location of each word. Okay, so the physical address is an integer in the range of 1 to n minus 1. Now, what is n? N is the size of computer memory. Now, what is size? N basically, if I say computer memory has a size n, basically it means that memory contains n words. Okay, so let's say if I say n is 256. Okay. Now, why I use 256? Because 256 is 2 to the 8. So typically, when we talk about computer memory, computer actually size, we tend to use the number which is a power of 2. Okay, because the computer used the binary numbers. Now, if that's the size of the computer memory, n is 256, that means that memory contains 256 words. So now, the physical address is an integer that identifies a word in the physical memory of size n. Okay, so the address typically comprises a fixed number of bits. Okay, now for memory of size n, so that means I need a binary numbers to represent, the memory address of size n. So what's the range of the memory address? For size m, the memory address is going to be, say, from 0 to 255, right? So if the size is n, let's say that's a memory, it's n, the size is n is 256, right? So then the actual memory going to be, looks like this. Each represent a word. So this is word number 1, that's another word, that's another word, and then we have total of 256 words. Okay. Now the memory address is the physical address is the integer represent the location of the word of a word. So the first word is at the location 0, second one is 1, and that's 3, and all the way to with n of 256. The last one going to be 255 because we start from 0, right? Now the question is, the memory address, the physical address actually start from 0 to 255. Now, how many bits, the number of bits do I need to store up to 255? Now, if you know the computer binary numbers, then we know for 255 is 2 to the 8, right? Okay, so the answer is the memory of size n, which is 256, requires an address size of k. Now, what is the k? The k is equals the I need to find a k such that the n equals 2 to the k. So that's 256 equals 2k. Now, what is that number? Now, that's why I used the power of 2, because 256 is 2 to the 8. So what is a k? K is 8. So I need 8 bits. 8 bits to store a physical address for memory of size 256. Okay, store a physical address for memory of 256. If the memory size is 256, I need 8 bits to store this. Why? Because with 8 bits, you can represent total of 256 different numbers from 0 to 255, right? Now, what is the 0 in 8 bits representation? So that's 0, 0, 0, 0, 0, 0, 0, right? Now, what is 255? That's 1, 1, 1, 1, 1, 1, 1, 1, because each bit can either be 1 or 0. And this bit could be 1 or 0. So each bit have 2 choices, right? So you have a total of 8 bits. So the total number of different with 8 bits, I can represent total of 2 times 2 times 2 times 2 times 2 times, total of 8 times, right? So it's actually 2 to the 8. Okay, so it's actually 2 to the 8. Okay, so that's the reason why a memory of size n requires an address of size k, where k is satisfy n equals 2k. So in another word, a memory of size 256 requires an address of size 8, because 2 to the 8 is 256. A computer system has a single physical memory, and that single physical memory has a fixed size. Okay, we measure the physical memory using the word, which is the smallest measurable unit for the physical memory. For example, in this case, this physical memory has n words. Now, each word could be like 4 bytes or 8 bytes or 1 byte. Okay. Now, in this case, it has n word. Now, each word corresponding to a physical address, like a 0. Here it's a 99, and here's a 500, 627. So each number represents the address. It just basically tells the location of this particular word in the physical memory. Now, to facilitate program development and programming loading, we're also going to introduce another concept. It's called the logic address space or logical memory. Logic address space is an abstraction of physical memory, consisting of a sequence of imaginary memory location. So it's imaginary memory locations. Now, each logic address also has a range from, for example, from 0 to n-1. So that means this logical address space contains m words. Now, the size of the word for the logical address space should be the same as the size of a word for a physical memory, because it's basically an abstraction of the physical memory. Okay, so m is the size of the logic address space. Now, actually, multiple logic address spaces are provided with possibility of different address ranges. So that means logical address space, is not unique. It's not like a physical memory space. There's only one physical memory. Okay, but we may have multiple memory space. For example, in here we have one memory from 0 to m-1. The other actually logical memory also from 0 to m-1. But the truth is that you may have a logical memory space that from 0 to maybe k-1. Okay, it doesn't have to be the same size like this case. Okay, now for when you develop a program, so in order to actually make it easier for people to manage the program development, then you can develop a program and place the program in a logical memory space with a logical memory address. For example, this program takes 128 words, right? So once you place in a logical memory address, it's starting from 0 to 127. It's 128 minus 1. And we may actually develop another program. You're going to actually start from the logic address 0 to 299. So now, this 0 and the 127, that's a logical address. Now, for each, for example, a statement in the program, it takes a logical, it's placed in a logical word and has a logical memory address. For example, this is probably logic address 100. Okay. Now, typically, the logic address basically measures the location of this particular word to the beginning of the logical space. So for 100, that means it's a distance from the logic address 0 to this logic address. So it's 100. It does not represent the actual physical location because we haven't actually mapped this program into the physical memory yet. Remember, when a computer system tries to run a program, you first need to load the program into the physical memory. So then the CPU can fetch the instructions for the program and start to execute. Now, the idea for the logical address space is that we can actually, schedule the, organize the program in a logical memory space before we actually load into the physical memory. Okay. So now, once we decide that we want to actually map the logical, when we try to load the program into the physical memory, and then we basically need to map the logical address of the program into the physical address. So we need to find out a free space in the physical address. For example, for this program, it takes the logic address from 0 to 127. So we first need to actually put this one in the in a disk space and then based on logic addresses from 0 to 127. But when the program is actually loaded into the computer memory, the physical memory, you don't necessarily load the logical address 0 into the physical address 0. Because remember, you may have a multiple logical space, and each logical space has address 0. But when you try to map a multiple program into the physical memory, you cannot load the program all into the memory space 0 in the physical memory space, because there's only one physical address 0. So that's the reason why we need to locate, okay, here is the free space in the physical memory starting from memory address 500. So basically we map the logical memory 0 to physical memory 500, and then we also map the corresponding logical address to the corresponding location in the physical memory address. For example, 127 going to be mapped to 500 plus 107, which is 627. Okay, same thing with another program in another logical space. So we can actually, the logical address is 0 and to 299. So when you load into the physical address, okay, if we cannot find a physical address space that's big enough, a consecutive physical address space that's big enough, so there's a possibility that we can split the logical address into two pieces, and we load the first part to the physical address space 0 to 99, and then we load another piece from 100 to 299 to another space. So we map 100 to 700, and then the corresponding logical address space is going to be mapped to the corresponding physical address. So 299 going to be mapped to 899. Okay. So that's the reason why we introduce a logical address. So logical address is an integer in the range from 0 to n-1 that identifies a word in the logical address space. Okay. Now prior to execution, so that means before we actually try to execute the program, a logical address space is mapped to portion of the physical memory, and then the program is copied into the corresponding location. Okay. So once I actually map the first logic address 0 to some location, and then we can map the follow-up. Okay. So now let's talk about the program transformations. Now in early computer systems, people created a binary code, and also known as machine code, and then loaded the machine code directly into the computer memory and executed it. Now, as the computer becomes more and more powerful, programs becomes bigger and bigger. So it's so difficult to manipulate this binary code now. So then people start to write the computer program using symbolic languages such as C, C++, Pascal, Java, or even Python. They use various different languages, and these are called high-level language. And also people, in the early age, people used assembly language, or for most of the, double E majors, they use the assembly languages. This assembly language is also a symbolic language. Now these language must be translated by something called a compiler or assembler into executable machine code. Now compiler or assembler is also a software. That this piece of software are used to translate the symbolic language into the machine code. Okay. So now we have, so for each program, we may have to create, the source module. Now, one program may contain a couple of source modules. Now, then I call module 1, module 2, source module 3. Now each of the source module are going to become, translated into the next one called the object module. Now object module is it's actually a machine code. Object module 2, these are machine code. Now, the object module could be self-contained, and you can directly run it. But it could be, used to actually link it together to create something called a load module. So each object module could be just one small part of the program. So they have to be linked together into something called a load module. Okay. So the first one they need to actually, translate into the object module, and then link all the object module together to create the load module. And then you can load the load module. That's the final version, which is a binary code or machine code into the memory. Now, when you execute the load module, so then when you execute the actually program, so you may actually need to link to the code in the library, right? So this is how you're going to do. So now we introduce the three concepts. One is source module, which is actually a program written in symbolic language, and then after we compile the source module, then it will translate the source module into the object module, and then after we link the object module, then it becomes load module. The load module is the final code that we can directly load into the computer system. Okay, so let's summarize what we talked about in the previous slide. So first, a program consists of one or more source module, and then each module is translated into the object module by compiler or the assembler. So then the object modules are combined into a load module using the linker. Okay, using the linker. The load module is kept on disk, and also we call this executable code. So the load module is copied to the physical memory by a loader. So now it's ready to execute. Now, during the execution, the various system libraries in the form of object module may be included in the load module by linker, okay, or by the loader, or during the execution. There's a various different way. Sometimes the library code is going to be, linked during the linker time, or the loader time, okay, or during the runtime. So we know that in the program transformations, a program may have multiple source modules. Now, each source module is going to be transformed into the object module using either the compiler or the assembler. Now then, these object modules are combined to create a load module using the linker. Now, the load module eventually going to be loaded into the physical memory, and during that time, all the logical addresses basically bound to actual physical address in memory. Okay, so before the actual loading, everything's actually in the logical address space. Now, each module, like object module, may have its own logical address spaces starting with address 0, and this one has its own logic address space starting with address 0. So that's why during the link time, the logical addresses of instructions and data may be changing, even it's a logical address, because you combine all these modules in a different logical address spaces into one logical address space. So there should be only one actually memory address 0. So you cannot have multiple memory addresses 0, right? So only during the final step of programming loading, the final step of the program loading, are all logical address bound to actual physical address in memory. Okay, so during the program transformations, a program component may move from one address space to another. Now this is called a program relocation. Now the relocation may be between two logical address space if before the actual load, okay, or from logical address space to the physical address space during the actual load to the physical memory. Now there are two types of relocation. The static relocation binds all logical address to the physical address prior to execution. So that's sometimes also called a compiler time relocation. Now, the other one is called a dynamical relocation. So dynamical relocation postpones the binding of the logical address to the physical address until the addressed item is accessed during the execution. Now that's also called runtime relocation. Now let's take a look at the example. Okay, so let's say so there's a program which consists of one module, source module. The program may have some other modules. Okay, now that's one of the source module. Okay, so that module basically defines a variable I, and then later it gonna assign a value. Also, the function f is also called, but the function resides in different module. Okay, so let's say I declare I as an integer and then assign I equals some value, and I call a function. The actual function is residing in another module. Okay, so we're gonna link this during the link time. Now, after you compile the code, so the compiler assumes a logical address 0. Okay. The logical address 0. And assign I to address 20. So I gonna assign a value which is located in the memory address 20. The logical memory address 20. Okay. So then I gonna use the instruction called a store. Store. Okay. The store instruction store then reference location 20. And then I can actually, make a call to F. Okay. So that means I'm going to call a function, okay, F, which is defined in some other places. Now that's the object module. Okay. Now we know that the function F is not defined here, defined elsewhere in another module, right? So now the other module will be eventually linked to this module during the link time. So after the link, then we're going to create another logical module. But in this case, we're going to actually combine the other module which defines the function F. Okay, so let's say it's a function F. So maybe it's defined here, right? Okay, so in here. So that function, the module that contains the function F, basically we're going to reassign the logical address. So the function F gonna actually, the module that contains the function F gonna be assigned the logical address from 0 to 100. Let's say 99. And then the module that defines the variable I gonna start from 100 to, let's say, I don't know, maybe depend on this value, right? If this is actually 1000, then this is going to be 1100. Okay. So now in this case, you're going to actually change the logical addresses, right, for different instruction. So now because we start from 100, so then the previous logical address 20 becomes 120 because it's this one actually in the new logic address space, it starts from 100, so you're going to map to 120. So the I, the store, actually initially stored to 20, now it's stored to 120. Okay. Now when we call the function, now this time it's not a stub anymore. So it actually has the address. So that's a logical address 0 because the function F is not a stub anymore. It's actually has a logical address 0. So we call 0. So that means when you call 0, it starts to execute the memory address here. Okay. So that's a load module. Okay. So now these are still logical address, right? Now, when we actually load the module into the physical memory, then now suppose that we locate the physical memory 1000. That's the physical memory address. We're going to load this, the logic address 0 to the physical address 1000. And then this 100 becomes 1100, right? So up on this one. And then 120 becomes 1120. Now that's where the actual value located. That's the physical memory address that contains the value. So when we say store actually reference the location 20 at 120. Now we reference the location 1120. Okay, so now the function call, it was called 0 because 0 maps to 1000, so it's 1000 now. So everything actually, the logic address is going to be add 1000. So we map to the corresponding to the physical address. So this one going to map to 2100. Okay, now that's the load module in memory. In the memory. Now this is called a static load relocation, because once we actually load everything is actually all set. We don't have to change anything. Now, what is a dynamic loading? Dynamic loading is slightly different. Okay, so let's say I'm going to squeeze some space here. So if the loading is dynamic loading, okay, so let's say I'm going to load it dynamically. Dynamic loading. So then, I'm going to actually load this thing to the physical memory space 1000. Okay, now that's still 1100. And then during the dynamic loading, so this is actually supposed to be the memory location that stores the value for I, and this is st. Because it's dynamic loading, so during the load time we actually don't change the corresponding address. We still actually stays that way. And the call function, we still call 0. We still actually call 0. We don't call 1000. We don't actually decide which, eventually where's the function located in the actual physical memory until we actually run this code. Okay, when we actually run the code call the function, then we decide dynamically which physical memory going to be. Okay, so when you actually call this statement, then you're going to actually perform the dynamic loading. So it will start to add 1000, because when you load, memory address 0 becomes 1000, right? So then we're going to actually add 1000 for each corresponding logic address. So then we can refer to this by, adding 120 by plus 1000. So you're going to actually get the 1000 and the 120. Now when you call 0, then you're going to actually, during dynamic binding, then you're going to basically change the logic address 0 to 1000. So you're going to actually call 1000. But this is actually, this two action happens during the runtime, not during the compiler time, during the load time. Okay, so that's a difference. That's a dynamic loading. Okay, so here's a summary of the program relocation we just talked about in the previous slide. Now, so we talk about a static relocation. So we just actually transfer from the source module to the object module, and then to the load module, then to the load module in the memory. So just pay attention to the logic address change. Okay, it's, object module, the logic address start from 0, but in the load module, the logic address actually changed from 0 to 100 and from 20 to 120. And we just link, once you link the other module which contains the function, we need to place the other module in the new actual logic address space. Okay, when we do the loading, we actually map the logic address to the physical address. Now this is dynamic loading. Okay, so that's a dynamic loading. Now during the loading time, we only load, each of the instruction in the logical address into the physical address, but we don't actually change the logic address inside until when we actually execute this statement, then we actually perform the dynamic logical to physical address translation. Okay, so that translation should be very simple, and we'll see actually later on. Okay, thank you.